Hey everyone, so today we're going to be doing a question called maximum number of points with cost. Let's take a look at the question. You are given an m by n matrix, okay, called points. Starting with 0 points, you want to maximize the number of points you can get from the matrix. To gain points, you must pick one cell in each row. Picking the cell at coordinates RC will add points RC to your score. However, you will lose points if you pick a cell too far away from the cell that you picked in the previous row. For every two adjacent rows, R and R plus 1, picking cells at coordinates RC1 and R plus 1 C2 will subtract the absolute value of the difference of C1 and C2 from your score. Return the maximum number of points you can achieve. So for example, if we're given this m by n matrix, right, we want to find the maximum number of points that we can accumulate through picking cells, one cell at each row. Now, the caveat is that, if you choose a cell, for example, 3 at the very beginning, right, because it's the largest number, if you choose a cell in the second row that is directly below it, we're going to subtract 0, right? Because it's going to be the same column. However, if we move one row towards our left here, we're going to have to subtract 1 from our total. If we chose this value here, whatever it is, then we'd have to subtract 2 because it's 2 cells over from the last column in our last row. So on and so forth. If we chose 3 here, because our last cell chosen here is in the second column, we'd have to subtract 1 because we're moving one column over. So in total, the sum of this would be 3 plus 5 plus 3 minus 1, because 5 is 1 over from our last row here. And then we'd have to subtract 1 again, which is 1 over. And so we basically have to maximize this, right? So in this case, if we walked through it, it's 3 plus 5 plus 3, like I said before. However, we have to subtract off the offsets here, okay? Similar, here we're choosing 5. We want to add 3 to it, which is great because we don't have to subtract any values because they're in the same column. And then we'd have to add 4 here, but we'd have to subtract 1 because it's towards the left. So how do we even begin to think about this problem? How do we, what techniques do we have that can help to guide our solution? Well, one thing to notice is that it's asking for the maximum number of points you can achieve. Often when you're dealing with finding the maximum of something, you're going to want to employ dynamic programming, okay? Which means that we're going to be looking at subproblems and building our larger problems off of those subproblems. So if we kind of take a look at our matrix here, which is, ripe for the use of dynamic programming, because basically a matrix is just an array of arrays, right? So if we kind of take a look at our situation here and we use dynamic programming, okay, we can kind of look at the base case as being this top row here. Because if we're just given a 1 by 3 matrix, right, the maximum number of points to be achieved is simply the largest number in that row, so which would be 3. It gets tricky then when you start to work on the subproblems where you have the number of rows being larger than 1. So for example, 2 rows, right? So in this case, we have to start thinking in terms of, okay, if we chose 3 here, okay, if we chose the largest value here as being if we chose this value, or this value being the largest value, then for our value here, what would be the best, most optimal solution, right? What would give the maximum number of points? Well, if we think about it, right, if we're dealing just with one here, and we don't yet know which one of these is largest, right? Or which combined with this value will be largest. What we'd have to do is we'd have to take a look at assuming that, okay, this cell is going to be chosen as the largest, let's say. If that's the case, right, then what does this value equal? Well, it equals 2. If I chose 2 as the largest value, so the second cell, what does this value equal? Well, it's 2 plus 1 minus the offset. And then similarly, if I chose this value, it'd be 3 plus 1 minus 2, right? Subtract off the offset because it's 2 columns over. And then if we take the maximum of all those values, then we have the maximum value here. Similar to here, we'd have to make an assumption that, okay, if this value here in the first cell is the largest value, okay, and we add it to 5, then we'd have to subtract off 1, right? And we'd get a value. Here, we'd add these two values together and we'd subtract off 0 because there's no offset. Here, we'd have to add these two values and then subtract off 1, which is the offset, and we'd find the max value, and so on and so forth for the entire row, right? So that's a lot of work if you think about it. And in fact, the runtime for that is O, if we think about it, right? Sorry, a lot of zooming here. The runtime for that would be O, we have m by n squares, cells. And for each of these cells, we basically have to do n calculations. So it's times n, right? Because we have to take a look at n number of possible maximum values and then add them to each cell. So that's why it's O times m times n squared, right? But this is not a great runtime at all. So how do we kind of simplify this? Well, we would simplify this by observing that essentially, we can use left and right accumulators, which is a different kind of way of approaching these sorts of problems where you want to find the maximum value depending on what's going on the right side and the left side. And admittedly, this is a bit tricky. It's not, for me, it wasn't entirely intuitive to walk through this. So let's kind of take a look at how this might sort of start, right? So we have, and I'm just going to draw this out before we even begin, 1, 2, 3, 1, 5, 1, 3, 1, 1, okay? So this is our, beginning matrix. If we kind of look at sort of any, if we start off with taking a look at this and we call it previous, right? And we have a current array, which is at the very beginning empty, and it's size of 3. If we take a look at, let's say, for example, since this is previous, and now we're working kind of on this row, right, to determine the max, let's say the max sum, okay? Instead of doing all of that work where we are, taking a look at this value and then adding 1 to it and then subtracting 0 and then 2 added to 1 and then subtracting 1. So basically all of that crazy work that we did before, instead of doing that, what we can do is we can have left and right accumulators that move this way and this way. And then we choose the maximum of what's happened for a cell. And the way that we can see that is that with this maximum accumulator on the left side and this right maximum accumulator going on the right side, our value, let's say we're looking at 5, is simply going to be the max of the value calculated for our left and right accumulator. So let's say this is left max, this is right max, that has been accumulated thus far. So how do we do this, and what does this look like? Well, if we take a look at, let's say starting off with this value here, okay? If we imagine that there's like a 0 value here, and we take a look at adding 0 to 1, so let's assume this is like a null, this is like a phantom column, right? 0 minus 1, sorry, 0 plus 1 minus 1, because this is the offset, right? It's in this phantom column, which is to the left of 1. We want to find the max between this value and 1 plus 1 minus 0, right? So this would be 0, and this would be 2. So the maximum would be 2, right? And we do the same thing for 5 here, right? We take a look at what's going on here and here. So this would be the max between 5 plus 1 minus the offset, and then 5 plus 2 minus 0. So the max between these two values is simply 7, right? And then we take a look at, for this value here, right? 1 plus 2 minus 1, or 3 plus 1 minus 0. So that's 4, okay? So the left max values are 2, 7, 4, right? So if we take a look at, if we do this kind of in reverse on the right-hand side here, right, we'd get something like, and we imagine that there's this phantom 0 column here, right? We would go, what is 1 plus 0 minus 1, right? 3 plus 1 minus 0, so that's going to be 4, okay? And that makes sense, right? You can see that 3 plus 1, if we're just dealing with the right-hand side here, everything that's going on the right-hand side here, then we see that the max value is 4 here, right? Then we deal with 5, right? Okay, so 5 plus 3 minus 1, or 5 plus 2 minus 0. So this is going to be 7, right? And then here, 1 plus 2 minus 1, or 1 plus 1 minus 0. So it's going to be 2. So in both cases, so this is left, right? This is right. If we take the max of these values here, right, then we have our max row, or rather we have our max row, the maximum solution for a row, a matrix that has, just these first two columns. So it would be 2, 7, 4. And if we kind of think about it logically, right, we have 1 and 1, right? So if we take the max of the two going left and the right for any one spot here, right? So let's actually look at 5, right? So here we're taking the max of 7 and 7, right? What we're doing is essentially this is so hard to explain. Forgive me. Let's actually just dig into the code. Okay. So oh, right. Okay. So the reason why this works is because imagine that we are dealing with a situation where it's like, let me just draw this again. 1, 2, 3, 1, 5, 1, 3, 1, 1, right? So we have these left and right maximum accumulators, right? So we're going left, and then we're going right, and then we're comparing the values that come from it, and we're finding the max, okay? And that gives us our next array, right? Now, the reason why this works is if you think about it, right? Let's say we have 51 here, right? And let's say this is 10, okay? So clearly, right, if we're trying to build our next subproblem, the solution for our next subproblem, right, the maximum value is really going to be 51 plus 10 minus 2. So we want to move this 51, we want to find a way of moving this 51 over, right, as we left accumulate. So if we, in order to do that, right, as we're moving towards the left and as we're moving towards the right, we always want to be taking a look at the last value that we added. So for example, if here, right, the max value that was added was 51, right, and we want to somehow populate this forward in our left accumulator, then we're going to want to find the math.max of 51 minus, you know, whatever minus some offset, right? And the possibility of whatever is here. So for example, this could be, you know, let's say if this was 200, right? So we don't want to move 51 forward, we want to move 200 forward, right, into the next iteration. Similarly, we want to move the max value going from our right-hand side to our left, right? So when you find the max of both of them, you're really finding the max of all of the sums that happened towards the left of a value and then towards the right of a value. And then you're finding the maximum of the two, which gives you the maximum sum possible for any one spot. Okay? So it's a little tricky to wrap your mind around, but that's the general logic. So let's walk into the code, because that's where, you know, we're really going to see this in action and learn how to, you know, code this out. So, right, just like any matrix question, we want to really grab the rows and the columns first. So points dot length const calls is points 0 dot length. Okay, so let previous. So what we want to do is this, right? So like I said before, you know, we're going to use dynamic programming, right? But what we know with dynamic programming is that you can either require, let's say, for example, the entire matrix, right? So another DP matrix which holds a spot for every single cell. Or if you know that your subproblems, the current problem that you're on is dependent on a predictable subproblem. So for example, you know, we have this really just depending on the previous solution, right? Then what we can do is we can just have a previous and a current. And in this case, right, our previous and our current are just going to be arrays, right, within our matrix. So the first one is going to be previous, and it's going to be pointing at the very, very first row in our matrix. And then our current is just going to be a new array, right? And it's going to be length columns, right? That kind of makes sense. And what we're going to do is we're going to initialize our accumulators, okay? Or rather, we're going to initialize two arrays, or rather two variables that are used in our accumulators, and that's going to be max left and then max right. Now what we're going to do is we are going to move through every single row after our first row. Okay. And what we want to do here is we want to build our left and our right accumulators. So let's do our left first, right? And this is going to be in relation to columns, right? So we're going to use this max left variable, which is, like I said before, it's going to be the variable, the highest, let me see if I can use this. Oh, how do I move this? Oh, sorry. Give me 1 second, trying to manage this. How on earth do I move this across? Hope you saw the other part of this screen. Oh, right, great. Okay. So basically the max left is going to be whatever max value it is that we currently have, and that we want to sort of move along this accumulator path. So max left really then is equal to math.max of our previous max left, and we want to subtract 1. And the reason why we want to subtract 1, actually, these should be initialized to 0, right? The reason why we subtract 1 is because depending on which column that we're currently at, so if we're at this column or this column, we want to keep in mind that as we move, further away from from its original origin, that we're subtracting 1, because we have this condition to subtract 1 when we're moving between columns as the offset, right? So we have this -1, and we have previous of j. So if we're working with this here, right, we want to know, okay, is the max left value going to be this 51 minus 1, so 50, that we add with 5, or is it going to be this 200, right, previous j, right? So that's what this is, right? We want to know which one. And then what we want to do is in our solution, we want to add max left plus points ij. And that's just, for example, in this case, that would be this 5, right? If we're working with this first row. So it's either going to be max left minus 1, so 51 minus 1, or it's going to be adding, so you're adding that, so 50 plus 5, or it's going to be 200, so what's directly above this 5 here, right? So that's why you have points ij here. And then likewise, so this is our left accumulator, right? And this is our right accumulator. So now we're going from the right-hand side to the left. So let j is equal to cols minus 1. J is greater than or equal to 0. J minus minus, right? And now we're going to use this max right. So similarly, max right is going to be equal to math dot max of max right minus 1. For this, we're subtracting 1 for the same reason that if we're always looking back 1, right? Always looking back 1, then we have to subtract 1 from the largest value that's being brought over. So for example, if the largest value that's being brought over is 3 here, then we'd have to subtract 1, right? And add it to 5, which makes sense, right? 5 plus 3 minus the offset is 1. So that's why it's max right minus 1. And then we have previous of j, which makes sense, right? So either we are adding whatever value is being populated from the right side over, or it's previous of j, right? Just like it was up here. So what this means then is we have current of j is equal to, and then here we have our finding the maximum, right? We're going to do a little cheat a little bit. We're going to find the max of the two based on our what is currently stored at cur j. So we're going to do cur j, which came from our left accumulator, or we're going to take a look at what's going on the right-hand accumulator side, which is just simply max right plus points ij. Again, points ij references the value above it, right? Or rather, the value that we're currently at, right? So that's what this points ij is, right? The value that we're currently at. Oh gosh, this is a lot. Okay, so let me go over this again, right? So max left is equal to max left minus 1, right? And we have to subtract 1 because we're moving the maximum value to add on the left side. It's like we're kind of moving that value along in our accumulator, and we always have to be subtracting 1 because it's going to lag behind our current value, right? Similarly, on the right-hand accumulator, we have this minus 1 as well because it's always lagging behind, right? And we compare it up against previous j, and in this case, previous j is going to be in this case, if it's 200, so the one directly above it, it'd be 200, right? For the left-hand side. So it's whatever is sort of like directly above the current value that we're at, that we're calculating. So that's why it's previous j, right? Here, we want to figure out what's the max that we want to move forward. Is it going to be this, or is it going to be the max left value here? Similarly, on the max right side, is it going to be this, or is it going to be the max right addition that we're moving forward? Then what we do is we set cur j, okay, is going to equal to the value that's maximum that has occurred here on the left side, plus points ij, so the current value that we're on in the matrix. Likewise, on the right-hand side, we are going to calculate that value, 5 plus, whatever is the max right accumulator value. But we want to find the maximum between the left accumulator and right accumulator. Well, what's already in the left accumulator at cur j is what is the max accumulator on the left-hand side that we've already calculated. So that's why we have this extra math.max of cur j and then max right plus this value here. So after this is done, right, we want to move our pointers forward. We want to create a brand new array for current, and then we want to reset our max left and our max right, right? And then at the very end, right, the values within previous, right, we want to find the maximum of all of those values, right? And that just becomes then our answer. In the same way that, for example, here, oh, shoot, still getting used to this. Where is it? Right? In the same way that if we just had 1, 2, 3, 1, 5, 1, right? And this is our subproblem, right? Or rather, this is our final sort of row. We'd want to find the max value. So it'd be 7 here. And that would be the maximum possible sum, right? The maximum number of points. And that makes sense if you kind of look at the original solution. If it's just 1, 2, 3, 1, 5, 1, the maximum would be 7, because take a look at these values, right? It'd be 5 plus 2 is 7, or it would be a combo of 5 plus 3 minus 1 would be 7. So let me submit this, right? So let's take a look at the time and the space complexity. So space complexity is pretty easy. It's going to be O of n, right? Because we have these two extra arrays, which are going to be dependent on the number of columns. So that's n. However, the time complexity, right? Let's take a look at that. Well, we have this for loop, which is going to be going through all of the rows. And then we have these left and right accumulators. Each are going to iterate through the number of columns. So that's n. So this is O of m, O of n, and similarly, this is O of n, right? And since this isn't a nested for loop, these are just two for loops beside each other, it's just basically going to be O of m times n. So that's our time complexity. Okay. So if you liked this solution, please do smash the like button. If you see some area of improvement, please do leave comments, and good luck on your interviews.